We are skipping chapter 4, which is on supramolecular chemistry. It's not that that stuff isn't important and interesting. It's just we probably don't have time for it. And it's a lot of crown ethers binding cations and then some other. Anyway, it's interesting enough, but it's sort of specific enough to that field that I thought we'd do other things. But you should feel welcome to go back and read it and learn more. And we may cover some of it later. So we're going to do chapter 5, which is acid-base chemistry. We're not going to spend very much time there because most of it's review of stuff in 351. Chapter 6 is stereochemistry. We're not going to spend that much time there. And then chapter 7 is kinetics, and there's a ton of stuff in there that's useful. So we may spend quite a bit of time there. I think we have an exam scheduled next week on the 21st. What's that?
The 20th and the 21st.
Is it the 20th and the 21st? Okay. Okay. Do you want it to be then? Do you want extra time? I mean, I'm flexible. I'm actually going out of town late next week to a conference, so I won't be around Wednesday or Friday.
Are we still going to pause?
No. I mean, I could get a sub, but I prefer not to. There are two things we might do. I could record lectures, or we could just skip them. Skip them.
If we have an exam next week, it'll basically just be everything we covered.
Since the previous exam. So that's, what the heck was chapter 2 about? I can't even remember. Nobody remembers?
Electronic effects.
The carbon.
Oh, yeah. Electronic effects and electronic and steric effects in molecular structure, and then non-covalent interactions.
Yeah, non-covalent interactions.
Yeah, I mean, it's a decent chunk. So
When would you move it to?
I'd maybe give you another week. I mean, do you want to deal with it next week or the week of Halloween? And I guess the other question is that we did the exam in writing down on the sheet format. Last year, as I think I mentioned, we did oral exams, which took, I think, a fair amount of time, but some people found useful. The way it would go is I would hand out the exam maybe 2 days before, and then you had to work by yourself, but use any and all resources to answer the questions. And then you had to come to my office and we would talk for like a half hour to 45 minutes. And you would present the answer to one question of your choice, and then I would choose another one. And you'd have to talk about it. And I would sort of assess your understanding from that conversation. So we can try that. It will just take time. So I mean, what we would basically need is a Tuesday or a Thursday, and then I would send out a Google Sheet, and you would sign up for a half-hour time sometime during the day to come talk to me. Well, I mean, I can do whatever the heck I want, right? Because I'm in charge. But if you want to try that, I'm willing to give it a shot. I think it's sometimes easier for me to assess your understanding when we can have a conversation than just on paper. So should we try that?
Yeah.
Okay, so that means the test will not be on the 20th or the 21st. I'm going to push it back a week. It'll probably be on, let's see, do we need a calendar? Calendar. Yeah, so let's plan on the 26th or the 28th. So what I will do is I will hand out the exam on the 25th, and then you'll have a couple days to work on it, and then I'll open up time on the 28th, and you can come talk to me. And what I'll do in terms of feedback is the same thing I did with your exams this time. I'll take notes during our conversation, and then I'll type up a little assessment, and I'll sort of rate your answers using the same rubric that I used for your written exams. And then you'll have seen it both ways and can sort of decide which poison you prefer, you hate less, I think is the, yeah. Okay. So we were talking about the hydrophobic effect. On the left here, we are sort of drawing what it looks like when a hydrocarbon is on its own. You have transient induced dipole interactions, but they are weak. I should press record. Did I already press? Oh no, we've been recording. We've been live for a while. Goodness, what did I say? Got to watch out for the hot mic. Anyway, the interactions are transient and weak. And because they're weak, there's a lot of disorder. Molecules are moving around without being held tightly to each other. Similarly, in water, we talked about how the hydrogen bonding interactions in water are stronger than the induced dipole interactions in the hydrocarbon solution, but there's a lot of entropy there because the water molecules are constantly changing who's bonded to whom. We switch very easily between a hydrogen bond and a full-on covalent bond. In fact, later on in the acid-base chapter, we'll learn that H3O plus is probably H3O plus and like 6 or 7 other water molecules, which is kind of crazy. So we talked about how in each of those states you've got decent interactions, which is enthalpy, favorable enthalpy, and then you have a lot of entropy. But when you dissolve the hydrocarbon in water, you remove some of the hydrogen bonding interactions that water would have had because the water molecules immediately surrounding the hydrocarbon, there's some space that they can't hydrogen bond with. So oxygen atoms and hydrogen atoms in the immediate vicinity of the hydrocarbon are not fully hydrogen bound. Because of that, the remaining hydrogen bonds will be stronger and those water molecules will be held more tightly in this sort of net or ice-like cage that surrounds the hydrocarbon. And so in other words, in going from like bulk water to water surrounding a hydrocarbon, you've got a fairly substantial loss of entropy. And that's what makes it thermodynamically unfavorable for a hydrocarbon to dissolve in water. Or alternatively, that's what makes it thermodynamically favorable for hydrocarbons in water to separate themselves out and not be dissolved in water. So this is why oil and water don't mix, because if they did, you would have to dramatically reduce the freedom and entropy of water molecules. All right. So I think, any questions about that? It's a fairly important concept. You might hear your 351 students, if you have them, saying things, getting questions about this wrong, saying things like, oh, well, oil and water don't mix because the oil is nonpolar and the water is polar and nonpolar don't mix. And that's just restating the observation. Why is the sky blue? Well, because it's blue, right? No, the real reason is what we've talked about in terms of what it takes to put a hydrocarbon in water and the reduced entropy of the surrounding water molecules. Now, there are a lot of processes that are driven by this. For example, the formation of micelles is all about getting nonpolar surface area out of water. Formation of lipid bilayers, same thing. And in fact, folding of proteins is in many cases related to getting nonpolar stuff not exposed to water. So if this is an unfolded protein chain, very conformationally flexible, but you have nonpolar groups exposed to solvent, and around each of them you have this ice-like cage of water molecules with reduced entropy. And we'll zoom in and we'll put one there. and it will be sad because of reduced entropy. That'll make you feel bad. But if the protein can rearrange its conformation such that the nonpolar groups are all on the inside, they will interact with each other on the inside, but it's not that that interaction is particularly strong. It's just that now you have a ton of water molecules that used to be surrounding those nonpolar residues, and we're free. They have maximum conformational entropy now. So this is a hydrophobically driven process. Now, processes that are driven by the hydrophobic effect have a unique thermodynamic signature. And this is a little bit tricky to explain, but I think it's important enough, and some of you may encounter it enough in your future that it's worth talking about. So going from an unfolded state for a protein, and the analogy here would be hydrocarbon in water. You see the relationship between those two situations. Before, we have just a hydrocarbon in water. Here we have hydrocarbons attached to protein and it's exposed to the water. And then down here we have the folded protein, and this corresponds to the hydrocarbon being separate from water. All right, and there's a free energy associated with this process, and it's favorable, so we expect it to be negative, meaning it's downhill in energy. And the reason it's downhill in energy is predominantly because of entropy, okay? Because you go from water having low entropy to going to a place where, anyway, afterwards you have high entropy of water. Okay, so that means if this process is favorable and delta G is negative, that means you're at a higher energy here than you are there. All right. You can, for processes like this, there are experiments you can do where you can calculate the enthalpy, and the entropy associated with that folding process. But there's another term in there, and that's the change in heat capacity. Okay, so a little bit of PChem, not too much because I don't understand it, but I don't know if you remember that learning in PChem that the first derivative of enthalpy with respect to temperature at constant pressure, that's where the P comes from, is heat capacity. Heat capacity is how much enthalpy changes with temperature. All right, that's just the basic definition. So let's examine what an alternative way of thinking about heat capacity is. How much heat must I add to increase the temperature of something? Okay, fine. You've maybe learned in junior high or high school that water has a high heat capacity. But let's examine that further, shall we? What is temperature anyway? What does that tell you?
How fast things are moving.
Right, average kinetic energy of the molecules. Okay, so if you want molecules to move faster, you add energy, right? But we've just spent all of chapter 3 talking about non-covalent interactions, these interactions that allow molecules to, well, interact with each other. And they have some energy that allows a complex between two molecules to be more favorable than two molecules separate. What that means is, if for example, you have two water molecules hydrogen bound to each other, this is a simple and dumb model, but if you have a hydrogen bond there, and you want to increase the kinetic energy of both of those water molecules, you're going to pump energy in, but the first bit that you pump in is going to have to break the hydrogen bond, and then you can make the molecules move faster, right? So in a lot of ways, heat capacity tells you how much more on top of molecular kinetic energy, how much more interactions you have. Because in order to raise the temperature, you first have to disrupt the interactions, and then you can increase kinetic energy. I'm not sure I said that right. Does anybody want to restate what I said so I can see if it sounds reasonable?
Yeah, I think you're just talking about to increase temperature, you want to increase kinetic energy of the molecule.
That's right. And if you want to increase kinetic energy of molecules, sometimes you need even more energy because you have to break apart the interactions that are holding them together. Yeah. Break apart the non-covalent interactions that are holding them together. Okay, so let's consider the situation before folding and after folding, or before dissolving the hydrocarbon, or rather when the hydrocarbon's dissolved in water versus when it's not. Let's think about the water molecules. I told you that these water molecules have relatively few degrees of freedom, and that their interactions with each other in the immediate vicinity of the hydrocarbon are stronger. So low entropy of water may be tighter hydrogen bonding in what we will call the first solvent shell. In contrast, here, water has high entropy and probably for those water molecules with higher entropy, probably weaker, more transient hydrogen bonding interactions for the liberated water molecules. Okay, let's think about how that would translate into heat capacity. For the unfolded protein, if I want to increase the temperature of the solution, some of the energy I'm putting in is going to have to go into making these molecules wiggle more. And it's hard to get them going because they're hydrogen bond tightly and they don't have a lot of freedom. Think of it this way. How many of you remember learning in high school that in phase changes of matter, for example, when ice is in water, what's the temperature of ice water? Anybody know? 0 degrees Celsius has to be, right? Because until all the ice is gone, all the energy you put in just melts the ice. It can't increase the temperature of the water, right? Similarly here, I told you to imagine the water in the immediate vicinity of the nonpolar groups as being an ice-like layer. So some of the energy you put in to increase the temperature, before it does that, it's got to melt the ice, okay? So you would expect maybe a higher heat capacity here because you have to melt the ice, by which we mean the layer of low freedom water molecules surrounding the nonpolar groups. In contrast, these water molecules that we liberated are now free, and there's no ice to melt. So we expect heat capacity lower because the ice-like layers are gone, and therefore there is no ice to melt. That means that when we go from something that has nonpolar surface area exposed to water to something that doesn't, we're going to go from something that's high heat capacity to something that's lower heat capacity. So we expect the change in heat capacity for going from unfolded to folded, we expect that to be negative. In contrast, if you are measuring the heat capacity of going from something that is folded to unfolded, you expect the change in heat capacity to be positive. And you can measure heat capacities for various processes using calorimetry. And in protein chemistry at least, and actually throughout physical organic chemistry, changes that have changes in water that have going from here to here that have negative heat capacity changes are often thought to be due to the hydrophobic effect. Yeah?
Okay, I might be stupid, but the higher heat capacity and then it goes to lower heat capacity, how is that negative if we're going from unfolded to folded? Because like the higher heat capacity, let's say are they negative numbers?
No, the heat capacities are, they,
because like if the unfolded was 100 and
yeah.
the folded was 25,
Uh-huh.
how would that be negative?
Because you take the final state, 25 minus 100.
Duh. Okay. Yeah.
Okay, that wasn't a stupid question, by the way. There's no such things. Yeah, you see it now. I think heat capacities are usually positive. I can't think of any case in which they're negative, but I could be wrong.
That's what I thought.
But a change in heat capacity can be negative. So if you're doing an experiment measuring protein folding and you see a change in heat capacity as the protein folds to become lower, that's consistent with a folding process that's driven by the hydrophobic effect. Okay. So I think that basically finishes us up on non-covalent interactions. There's a lot more, but I think you've got the foundation to deal with the things that you might encounter. Now we'll just move on to acid-base chemistry. So presumably anyone that's TAing 351 will have already been through this material. So let's just review. What does pKa mean? Your students are like, I remember I learned it in Gen Chem, but it was boring, so I forgot it.
It's like the log of the.
Okay. It's the pKa is minus log of Ka. It tells us about acidity. Okay. What is Ka? I'm going to be a 4-year-old and just ask why. What is Ka? pH is hydrogen ion, or hydronium is related to hydronium concentration. Good. Ka is what?
Is it like the concentration of the base divided by the other products to then by the reactants or something like that?
Yeah, you get Ka from this. Many people may not have explained it to you this way. Oh, come on, I charged it before class. We get the acid dissociation constant by putting acids in competition with water, and then we measure that equilibrium constant. Some people at this point tell me I'm cheating because actually equilibrium constants are not about concentrations, but are about activities, and activities of pure substances are 1, so we can neglect water, and I'm telling you no, and I don't care. So actually, because the concentration of water is high, around 55 molar in any solution of water, it remains constant, and you can multiply both sides by the concentration of water, and then you get the more familiar formulation of Ka. And in your general chemistry texts, they might have done this. I hate that because, of course, in water, there's no such thing as a free proton, right? But that's okay. All right. So Ka reflects, if you put the acid in water, how many protons does water pick up and how much conjugate base do you have versus your original acid. Incidentally, you can use these definitions of pH and pKa to derive a really useful relationship. You may already know this. If so, I'm sorry. Let's take the minus log of both sides of this equation and then take advantage of some logarithm properties. Minus log of Ka is just pKa. Logarithms say that the log of a product is equal to the sum of the logs of the individual items. So we can simplify this by, or why are we simplifying it? Because I want to turn this into pH. And then in general chemistry, I think a lot of students use this equation. They actually took this and put it on this side, and then they said, I want a certain pH. I know my acid has a certain pKa, so how much of the acid form versus the base form do I need to add to get the right pH of the buffer? And this is useful, and if you go into a lab that's doing biochemical experiments, you'll probably have to make some buffers at some point. So that's a decent application of this equation. A far more useful, to me anyway, application of the equation is the comparison of, it actually doesn't matter which way we do this. So pKa minus pH equals minus log of, it's hard to think in negative numbers and negative logs. So I'm going to take pH minus pKa equals log of, and if I'm, you can go back and make sure I'm right on the signs. I think I am. But this is a situation where, suppose you have an acid that's present in a solution where the pH is constant. In other words, you've already got a buffered solution and its pH, let's say 7, and then you put some group in that solution. You're not going to change the pH of the solution. Rather, the solution's going to change the protonation state of your acid. So what this tells you is that if the pH is higher than the pKa of a given acid, the acid will be mostly in its conjugate base form. Whereas if the pH is lower than the pKa of the acid should be mostly in its acidic form. And if pH is equal to pKa, this number goes to 0. The log of 1 is 0, right? So that means they have to be present in equal concentrations. This is useful from time to time. I like proteins, so as you can tell, so we talk about them a lot, but there are a lot of polar side chains in proteins, and understanding what their protonation state is important. So I'm showing you two different acidic forms of protein side chains. This pKa for this proton is about 4. And the pKa for this proton is, 11. We're pretending I know what it is. I think it's 11. Okay, and then we'll say we're in the body, in the cytosol, or in the blood. pH is 7.4. So, using this, tell me which form these two acidic groups should exist in. How about my carboxylic acid? So pH is 7.4. pH is higher than pKa. So this number is positive. What does that tell you about this ratio inside the log? yeah, the conjugate base form will dominate at this pH. So, yeah, the correct form, the pKa of that proton was 4. It's no longer there, so the correct form is the negatively charged carboxylate.
And the other one just stays
And the other one would stay as it is, exactly, right? Because 7.4 minus 11 is negative. That means that the denominator is the major contributor. So that's really useful. A lot of people struggle with it. And you don't need to, because it's, there's no need to struggle with protonation states of groups in biological conditions, as long as you know what the pH is and the pKa of the particular acid or base group. You're good to go. One thing that you may need to know to help your students is that in various biochemistry textbooks, they will show amino acid structures in their neutral forms. I had a student in my office yesterday asking about this, a former student, and he was like, you see this amino acid and you look at pKa's and they're given to you for that amino acid, and it's something like 2.1 and 9.2 or something like that. And he didn't know which was which. And the tricky thing is that this pKa 9.2 is actually for the positively charged amine and not for the neutral amine. And the reason that was confusing is, well, I don't know, actually. I think the textbook just prefers to show something neutral because whatever. But in reality, if it were talking about, if that pKa of 9, we're talking about going from the neutral amine to the negatively charged amide, that pKa should be like in the 40s or at least 38 or something like that. So you sort of have to know already that that's not what we're talking about. And for pKa's in the area of sort of 9 to 10 to 11 to 12, you're not talking about going from a neutral amine to a negatively charged amine. It's almost always going from a positively charged ammonium to the negatively charged amine. I don't know. You may not have struggled with that. That may be easy, but I've had students have a tough time with that before. All right. So much of what you know about acids and bases was focused on water. But of course, in organic chemistry, though water is important, we have a lot of other solvents. So I want to talk briefly about water. There's something your text points out called the leveling effect of water. And it's based on a couple of things. First, water is good at solvating charges. What do we mean by that? Well, via ion dipole or hydrogen bonding interactions. Water molecules can surround an ion and shield it from its counterion. This is why table salt dissolves in water, as we've already talked about. But what that means is that water may be better at stabilizing the conjugate base of an acid than another organic solvent would be. Second, water itself can be both an acid and a base. So if we're in water, we can't really measure the pKa of an acid stronger than hydronium. The reason for this, of course, is just acid-base chemistry. If you put HCl and water together and then compare conjugate acids and bases on either side of the equation, pKa of -9 there, pKa of -2. It's no contest. You get H3O plus. So actually, when you go down to the stockroom and buy concentrated HCl, what is it? It's H3O plus and chlorine. So you can't have any stronger acid in water than hydronium. So where did we get this number from? You can't actually measure the pKa of HCl in water. Where did we get it from? I don't actually understand the process, but it involves comparing compounds that you can characterize in two different solvents and then walking your way from solvent to solvent until you can get to measure the strength of the acid that you're interested in. Similarly, we can't measure the pKa of an acid whose conjugate base is more basic than hydroxide. Because, again, imagine taking tert butoxide. Its conjugate acid, tert butanol, has a pKa of 19. Water has a pKa of 16. So if you put tert butoxide in water, you just have hydroxide and whatever the counter ion is. Okay, so that's not such a hard concept to grasp, but based on these three considerations, an acid you might find yourself in a couple of different situations. An acid in organic solvent may be more acidic than in water, right? Because maybe its pKa is less than -2, so in water you don't feel the full effect of the acid. But if you go in organic solvent, maybe you do. Alternatively, an acid in organic solvent may be a lot weaker because water is good at solvating conjugate bases, and if you don't have that option, maybe something gets even less acidic. So is that useful? Is that a useful principle? Acids in organic solvent may be either stronger or weaker than they were in water. That's not a useful principle. There's not a particular rule of thumb, only that solvents change things. So I'm going to show you a few, changing solvents changes the strength of an acid. So I'm going to show you a few effects and we'll work on rationalizing them. So here I'm going to list a few acids and then we'll discuss their pKa's in various organic solvents. We'll start with acetic acid or vinegar. We'll do water, methanol, DMSO, DMF, and acetonitrile. And these are I don't know that we've listed the solvents in any particular order. In water, the pKa is about 4.8. In methanol, it's quite a bit less acidic. In DMSO, it's even less acidic, and it's even less acidic in DMF. Okay, so let's rationalize that. Whenever we're talking about how acidic something is, if we're talking about going from a neutral acid to a negatively charged conjugate base, it's almost always easier to rationalize the acidity of an acid by considering the stability of the conjugate base. All right, so what's the conjugate base of this acid? Negatively charged. Okay, so why do you think our pKa's go up so much as we switch from water to methanol?
The conjugate base is stabilized more